today. Of course, this week we started regression diagnostics, and of course, we're going to continue from that. So in today's topic, I call that overview of regression diagnostics. Give me 1 second. I think the weather is changing. Okay, so like I said, in the outline, I'm going to walk us through, some R codes, okay, that I call the further regression diagnostics R code. Then, then I'm also going to walk you through, to tell you that diagnostic plots may also be misleading. Okay, so I'm going to talk about that too. So let's look at the R code. Of course, I walk you through this R code on Wednesday. We're looking at the effects of, effects of experience on salary of professional workers. Okay, we got this particular data set, and looking at this now, this is the first case in the data. No, it's more than that. Okay, now we run the data, in statistical analysis. If I'm trying to look at the effect of one variable on the other, of course, I will need to first specify my model. And the idea of the model will come from the preliminary investigation that we conduct. Well, what is a preliminary investigation? It's basically going to be getting your scatter plot, right? Now, getting your scatter plot, you're actually looking at the effect of experience on salary. This is what you have. And this does not look like a straight line. You can see something like a curve. This scatter plot here is just a preliminary investigation. Now, if you ignore that and you continue, you decide to fit, the linear model, and you conduct a residual plot. Residual plot is, it's an investigation that we make, that we do after we've already estimated parameters in our model. Now, what I'm just trying to tell now is the plots. If you do the plots residual mode on experience, of course, this is basically what you're going to have. It means your residual is going to have a pattern. You remember, we use residual plot to investigate assumptions of linearity and constant variance. And this is so glaring that there's a linearity assumption here. I mean, there's a violation of linearity assumption here because of the fact that the residual plot is actually showing pattern. Okay, so you remember on Wednesday, I walk you through 4 plots, even though I said it's only 3 out of the 4 are very, very crucial. Some of you may be wondering, where do I get MOD? Of course, the MOD is actually here. Can you see that, the MOD? Let me see whether my iPad is going to work. Oh, okay, it's not writing there, but it's writing. That's actually favor those who are attending the lecture online. But it's also going to favor you because you may want to watch the recording at the end of the day too. So now you see the MOD, right? That's where the MOD come from. Okay, so if I do plot MOD, 1, that will give me a plot. MOD, 2, and we have another plot. MOD, 3, and we have so I'm actually going to have like 4 plots, and MOD, plot MOD1 is going to show residual plot. This is a residual plot. And what do we use residual plot to do? Of course, we use residual plot to investigate if assumptions of linearity and the constant variance hold. And for assumptions of linearity to hold, residual plot should show no pattern. What are you seeing now? That's a pattern, right? So we shall actually indicate violations. This is the explanation of that plot. Just to tell you what was plotted in the vertical axis and what was plotted in the horizontal axis. Of course, it's a plot of residual against the fitted values. How are you going to get residual? Residual is the difference between the actual response and the predicted response. Does that make sense? And that's exactly what you are plotting against the fitted value. The fitted values are the predicted values. So what are we trying to tell the world? There shouldn't be a relationship between the residual and the fitted. That's what we mean. No relationship means it shouldn't show any pattern. No pattern at all. Before we can use a linearity, before we can actually say, okay, linear absorption hold. What is the implication for that? If linear absorption hold, then that justifies the specification of linear model. I'm going to say that again. If linear absorption hold, that's actually justify, the specification of linear model. Okay, so that was why I said this plot can actually be used used to, I think I wanted to say identify, not identical. That my bad. So the plot can be used to identify the violation. You can change that to identify the violations of linearity and equivariance. And sometimes it can also be used to identify unusual observation. Okay. Now the next plot that I call plot mode, 2 is what we call a normal QQ plot. The normal QQ plots enable us to investigate whether there's a violations of normality of the error. One of the assumptions is that error should follow normal distribution. And before we can actually guarantee normality, we actually expect most of the point to fall on the diagonal straight line. Now, what is being plotted here? I try to explain the normal QQ plots. Okay, what do we have in the horizontal axis and what do we have in the vertical axis? In the vertical axis of a normal QQ plot, we got a quantize of the distribution of the standardized residuals. Of course, I've walked you through how residuals can be standardized. And in the horizontal axis, we got a quantize of a normal distribution. And I said this plot can be used to identify violations of normality. And how am I going to know if the normality assumption hold using the QQ plot? The better the dots adhere to straight line, the less the violation of normality. That's what we mean. Okay. Now the next plot that I want to talk about is a plot number 3. It's not that necessary in this course. I think I told you the other time. It's actually, this is a plot of the square root of the standardized residual to the fitted value. We could have a situation whereby before we can actually, we need to transform the residual. This is like considering this, trying to, you've already standardized residual, then you are still finding the square root again. That's like a double intervention to me. But, it's not that necessary in this course. Maybe in another course, we're going to discuss that in detail. Now, plot number 4 is necessary. When you do plot MOD, 4, where your MOD is actually what you used to name your model, then the plot number 4 will return Coke distance. If you take a look at this is a plot of Coke distance against the observation number, and of course, we can actually see some numbers that are outlying, depending on, but let me tell you this, even though we actually suspect some numbers to be outlying, then they may not be influential. They may not cause problem. And the only condition under which they can cause problem is when the Cook distance value is greater than 1. Does that make sense? I think I gave a threshold that when a Cook distance value is greater than 1, the observation that actually correspond to a Cook distance value greater than 1 will be regarded as an outlying point, and that may cause a problem. Even though at times we can see some outlying point, but provided their Cook distance is less than 1, there's no problem. Okay, so I think I just try to explain that, so it's actually there. Now, I also want to talk about outliers. You know, in addition to the assumptions that we have, assumptions of linearity, normality, constant variance, we also have assumptions of unusual observation, like outlier and high leverage. And of course, we got several ways of investigating for outliers. We can make use of the at values, standardized residual, and the Cook dot distance. But I'm going to say the Cook dot distance is very, very popular. But we can still use the standardized one. If you want to use the standardized one, we can put it as -2 to 2. If there is any observation whose standardized residual fall outside -2 to 2, can be regarded as an outlier. But do you know at times some researcher could extend this to -3 and 3? You know why? Because what you're actually going to refer to an outlier in your feed may not be outlier in my feed. And that's why at times they could actually extend that range. But if you want to go by Cook distance, then we're basically going to say an influential point is an observation whose Cook distance is greater than 1. So I think with Cook distance value, I think that is the Cook distance approach is more or less popular. Any question on all this? Any question? You super good, right? Okay. Now I want to go to the next objective of the day. You know, we call that diagnostic plot can be misleading. Of course, the same way judges in the court of law can also mislead. You know, at times we normally say, who judge the judges? You know, who judge them too? They need to be judged because they are not perfect. I know I don't pray to have a case, you know. You know why I don't pray to have a case? Because even though I have convincing evidence, judge is not perfect. And if two people are involved in litigation, okay, you don't have 100% of winning. Nobody has 100% of winning. And that is because, you know, the judge could be infallible. The judge is not perfect. So we have seen some, you know, when if you actually secure the services of an attorney and the attorney tell you that you have 100% of winning, change your attorney. If you say, oh, you have the 100% of winning this case, change your attorney. I want your attorney to be statistical in talking like, oh, you have more chance of winning this case. I'll prefer that to somebody who's telling me I have 100%. I cannot. So I want to go into a situation where diagnostic plots can be misleading. Okay. Now, to be able to, you know, show that I'm basically going to generate data. because I specifically want to generate some data that where there's a violation or not, where maybe I generated that from a particular, imagine if I generate data from normal distribution. I already know my data follow normal distribution, and I decide to use a diagnostic tool, and the diagnostic tool is telling me it does not follow normal distribution, then that diagnostic tool is wrong because I already know where my data set come from. Okay, because of that, I'm actually perform what I call the MCMC simulation. I'm going to consider both linear and nonlinear models along with a weak and strong linear relationship were simulated. So I'm going to work with small and large sample sizes. I'm going to consider like 50, 500. I basically want to test sampling properly to see the behavior of a diagnostic plot when sample size increases. Okay, so of course, 5 different scenarios will be put into consideration. And of course, I'm basically going to make use of our software. Now, I need you to take a look at what I'm actually displaying now. Now, if you look at what I'm displaying now, okay, I am actually targeting um, a simple linear regression model where I already know the beta is 2.5. If I want to simulate data, that 2.5 is my true value. That is not an estimate. That's a population value. That's what we call beta, not beta cap. Does that make sense? The 2.5 that I've already specified. Okay. Now, and I'm assuming my error follow normal distribution. Okay. I'm assuming my error follow normal distribution, which means 0 variance sigma squared. And the case that I actually, when I was doing my coding, I make sure that I use a sigma equal to 2. Of course, where does the sigma, if I really want to know whether the relationship is weak or strong, that depends on the standard deviation. Because what do you standardize to get correlation? You standardize covariance. Does that make sense? The correlation is the ratio of the covariance of X and Y to the product of the standard deviation of X and Y. So now, sigma equal to 2 means my variance equal to 4. So sigma equal to 2 is more or less a strong relationship. And if I start with n equal to 500 last sample, 500 is more or less considered last sample. Now we we generate my data set now, and we fit the model. And after fitting the model, we now decide to construct diagnostic plots. You can see the first one is a scatter plot. The second one is a scatter plot with a fitted regression model. The third one is a residual plot, and the fourth one is a normal KQ plot. Now, what implication do I actually have? Now, I'm going to say this. I deliberately generated the data set from normal distribution. When the data follow normal distribution, of course, I expect the error to follow normal distribution. The probability distribution of the error is the same as the probability distribution of the response variable. Does that make sense? If the response variable follow normal distribution, then the distribution of the error will also follow normal distribution. Now, based on what is being displayed now, okay, we basically want to investigate whether linearity assumption hold. Okay, but as you can see, okay, go ahead. For mixed effect model. Okay, in the case that's an entirely different. In fact, everything need to be follow normal distribution. I'm going to tell you what we follow normal distribution. If I'm talking about mixed effect model, like if factor A is factor A is random and the factor B is fixed, then if I want to investigate factor A because it's random, I will be investigating variability. Then I expect that factor A to follow normal distribution with the variance sigma square A. So that variance is different from the variance of the residual in the model. And that is why you may want to look at the contribution of that variance to the total variance. In that situation, you're going to have total variance. Variance of the random component plus the variance of the error of the residual, which is going to be sigma square A plus sigma square, right? You may want to look at the intra-class correlation. So the answer is yes, because the method you use in estimating the random effect model also assume normality, which is a method of restricted maximum likelihood. That's a good question. You took me to another, that is 4051. So I also teach 4051, apply statistics. Okay, now if you take a look at what is being displayed on the board, you're basically going to see there's no violation of linearity, right? Take a look at that. And there is no violations of constant variance. If you want to go by residual plot, look at the residual plot, right? So which means when the distribution is normal, right? And if you look at the normal QQ plot too, there's no violation of normality. Oh my God, our judge is doing a great job now, right? Because our judge took correct decision, because I already know that. But the question now is it because of the fact that the relationship that exists is strong, going by the value of standard deviation that I specify too, or is it because of the large sample size? Now the question now is, why can't we play around this? Now take a look at what I'm going to consider next. What I'm considering next, I'm considering the same model, right? But this time around, the sample size is small, 50 compared to 500. And at the same time, I made sigma to be 4. Okay, sigma to be 4. When you take a look, initially my sigma was 2. Now my sigma was 4, even though I still have a strong relationship, but the difference here is sample size. Okay, when I simulate data from a normal distribution and the sample size is 50 compared to when sample size is 500, we basically want to see whether the residual plot, the diagnostic plot, is going to do a great job. Okay, now we've plotted, we have the scatter plot, we have all the diagnostic plots, including the scatter plot, residual plot, and the QQ plot. Okay, as you can see. Okay, the very first thing, and I said something here, I said diagnostic plot may be misleading, especially when the sample size is small. How do I know? The residual plot shows a potential violation of equal variance. Do you see the residual plot? Can see those things are scattered away. If you take a look at that, the variance of residual along the x-axis is not the same. Therefore, there's a violation of that. Okay, but if you look at the QQ plot, okay, the QQ plot also show a violations of normality. Do you see the QQ plot? Okay, it shows a violations of normality. But let me ask you this question. But we have simulated from a normal distribution. Why a violations of normality by QQ plot? The reason being that because of the sample size, so which made the diagnostic plot also depend on the sample size. When the sample size was 500, you saw what happened. It took, and let me tell you this. That is the reason why at times some cases are delayed in courts. And delay or delay is not a denier of justice, because which means the courts actually need more time, like more sample size in terms of the numbers of witnesses they're going to call into the court. But in the long run, even though nobody actually wants his or her case to be delayed, but the facts remain that at times it could take forever to to basically take a correct decision. Okay, I think I just identify situation now where diagnostic plots may be misleading depending on your sample size. Now, another example, another scenario now, this time around, I want to go back to my sample size of 500. I'm simulating from normal distribution, but only that my sigma is so high. When a sigma is high, you know what that means? Even though relationship exists, the relationship is weak. Does that make sense now? So this scenario now, if I actually have, relationship exists but is weak, but the fact that we got a weak relationship does not imply violations of assumptions. Does that make sense? Now, when you take a look at what we have now, and that was why I said a weaker linear relationship doesn't equate to violation of assumption. A relationship could be weak. See, whether weak or strong, it's a relationship. That's what I mean here. So the fact that the relationship is kind of weak does not really equate to, oh, assumptions are violated. Now, let's take a look at, this now. You can see that everything stay okay here because we cannot see any violation. And maybe we're going to say, oh, maybe the reason why there's no violation is because of the sample size. You can also try this with a small sample size if you want to. Okay. Now, I want to go into non-linear model now. Okay, I've already identified a situation where a diagnostic plot could be misleading when you're working with a linear model, depending on the sample size. But what about, what is the situation like when I'm talking about non-linear? We got different types of non-linear model. Take a look at the model that I'm specifying now. Now, let me tell you this. I can be working with non-linear model and my data follow normal distribution. There's a difference between the probability distribution and relationship. Relationship could be occur in a linear way. It could occur in a non-linear way, but that doesn't mean that the error does not follow normal distribution. Some people have misinterpreted that. Whether I'm working with linear or non-linear, I expect my error to behave well. Does that make sense? So if error behaves well, error follow normal distribution. Okay. Now, if you take a look at this scenario, I got a non-linear model. Look at the model that I'm specifying. 10 sine x plus 5x plus the error, but the error follow normal distribution. Because how do I know the error follow normal distribution? Because I simulate data, okay, and it follow normal distribution, okay. Now, but the sample size is 50, okay. Now, I said diagnostic plot may not capture violations. May not capture violations with what? May not capture violations with this nonlinear model with a sample size small. Let's see. What do you see from the residual plot? What do you see from the normal QQ plot? And that was why I said residual plot and the scatter plot may fool the statistician to believe that linearity assumption is met. Take a look at the scatter plot. What is it suggesting? Linearity. But what module did I specify myself? What module did I? It's not linear. My diagnostic plot was not able to detect that I fitted nonlinear. Because take a look at the scatter plot. It's more or less like a straight line. It shouldn't be. Do you know this has fooled a lot of researchers, and that is why at times it looks as if our models are failing us, but our models are not failing us. We are the one that we're not doing the right thing. So, and that was why, I said, this is actually portraying to us that linearity assumption hold, even though I know my model that I fitted is not linear. Any question? Any question on that? Researchers should be careful. And that's why I'm happy that you guys are here. You are here because you actually, you need a statistical knowledge. Okay, now I'm going to go to the next one. Now, you don't know what happened now, right? I still want to work on the same model, not linear. And maybe the reason why the diagnostic plots may not be able to capture violations here is because of the small sample size. And I decided to do what? I increased the sample size to 500. Take a look at that. I'm still working with nonlinear. But what happened now? Oh my God. Look at my scatter plot now. Do you see my scatter plot now? Okay. So when you see my scatter plot now, I think it's trying to tell us that, okay, this may not be linear. You get what I mean? Okay. But I need you to look. I said, due to the violations of linearity, okay, now QQ plot is not a trustworthy tool for evaluating normality assumption anymore. Now, let me tell you this. In statistical analysis, okay, let me say this. If I want to start a case, where should I start from? Oh, I should start from Supreme Court? No, I'm not going to start from Supreme Court. I'll first go to maybe Magistrate Court or Federal High Court. Then if they take a decision that does not favor me, and I know that I'm right, then I will appeal to the higher courts. Now, let me tell you this. When you're working with linear regression model, the number one assumption is assumptions of linearity. If the linearity assumption fail, automatically, there's possibility. You don't even need to investigate normality. Because what guarantees normality is linearity in the first place. The linearity is more or less like if I use a model that capture a particular relationship, then my error will follow normal distribution. The reason why error don't follow normal distribution, why error don't behave well at times is because the model we specify does not agree with reality. When your model agree with reality, whether linear or non-linear, if you get the right model, then we expect the error to follow normal distribution. We expect the error to behave. Okay, now what I'm trying to say now, I said due to violation, when you take a look at this, when the sample size equal to 500, okay, there's a violation of linearity, right? If you take a look at what we're seeing now. But when you look at the normal QQ plot, okay, you're basically going to see that even if the normality hold here, but the fact that there's a violations of linearity, then it is not trustworthy to evaluate normality assumption. Why do I need to go to appeal courts? Okay, why do I need to go for normality? Why I know that the linearity is even in question. I think it's more or less like taking a case to a wrong court. Yeah, let me put it that way. Taking a case to a wrong court. What do I mean by wrong court? In the court of law, there's something that they call territorial jurisdiction. When somebody commits an offense in the state of Minnesota, and you try that person in the state of New York, even though the state of New York was able to establish the fact that the guy committed the offense, okay, maybe he's speaking the mind of the nature, whatever whatever decision they take in the state of New York is going to be declared null and void because the state of New York does not have a territorial jurisdiction. The same thing happened in statistical analysis, where I'm supposed to use a non-linear model. If I use a linear model, okay, then the linear model does not have a jurisdiction for that. Therefore, I don't even need to investigate whether assumption hold or not. When the premise of an argument is wrong, so be the conclusion. That's all it means. Take a look at that. Now, the last, do you know at times, how many more minutes do I have? Like 10? Okay, thank you. This is going to be the second to the last page. Do you know at times we deliberately simulate from a distribution that is non-normal? Let me tell you this. When the response variable follow normal distribution, so then the error is also going to follow normal distribution. That's fine. When the response variable follow gamma distribution, then the error should also follow gamma distribution. When I use gamma on gamma, it means I am using a module that commiserate with the reality. What we just want is using a module that go with the reality. Everything is going to be fine. Now, take a look at this now. I'm working with a linear module. I'm back at my linear module, but I realize the error does not follow normal distribution. Now the error follow gamma distribution. And I want the diagnostic plot to dictate that. What do you expect the normal QQ plot to tell me? That it does not, that is a violation of normality, because the error is not from normal, the error is from a different distribution. Now, let us see. When I set n to 500, okay, and that was why I said the QQ plot indicate violations of normality assumption. Indeed, we have defined the error with a gamma distribution. Now, when you take a look at what it means, that's a good decision. But if you want to try more, make the sample size, do this scenario, put the sample size to be 20. You will be surprised that the QQ plot may tell you it's normal. So and that is the reason why in statistical analysis and research in general, it is encouraged to work with a large sample size. And I know we are limited by budget, but in a situation where we don't have a large sample size, we have alternative procedure in statistics. It means we cannot seek redress using the parametric framework. We can go for non-parametric. We have non-parametric version of regression analysis. Okay, so I just wanted to take notes of that. The last page. Let's look at our conclusion now. A couple of notes on using diagnostic plots. I said diagnostic plots are more trustworthy when sample size is large. That is my conclusion. When sample size is large, that is when they are more trustworthy. But when sample size is small, they could be dangerous. Okay, that's what we're saying. And I said diagnostic plot may be misleading, especially when sample size is small or when data do not cover the entire range of X. When data do not cover the entire range of X, maybe we know the minimum. Like for those of you who are into measurement, you know the minimum, you know the maximum. But by the time you are dealing with by the time you are applying a model, maybe you did not, the data set you use does not cover the entire range of X. I'm going to tell you the diagnostic plot may be misleading. Then another important point is weak linear relationship does not equate to violation of assumption. We need to correct that. Some people will believe the moment the relationship is weak, then there's a violation. No. Does that make sense? So relationship could be linear or weak or strong. Of course, we know it can't be perfect because our model is not the same as reality. And I said diagnostic plot may not capture violations. It means at times there could be violations, but they may not capture that. And it's just going to report, oh, everything is fine. And that is dangerous because your recommendation, the recommendation you make from such model will be misleading. Okay. And that is why it's going to look as if, and whatever policy formulation based on that recommendation, we go nowhere. Okay. Now, violation of one assumption may affect the diagnostic of another assumption. What am I talking about? When linearity assumption is violated, then investigating normality assumption is not trustworthy. Exactly what I mean. Now, I think I put something here, principle. I said innocent until overwhelming evidence prove good. Of course, in the court of law, before it is assumed that the accused person is innocent unless it is proven by law, and which may believing that no assumptions have been violated unless there's a strong evidence in the diagnostic plot. Any question? Okay. This is going to be, oh, go ahead. Okay. It is not only diagnostical plots that we use. And the reason why we have some standard statistical tests is because of the fact that some of us, the way when we read from plots, we may have different interpretation. And that's why it's always good to always to go for a standard test, like a Shapiro wiki test. It's not only Shapiro wiki test. If I want to talk about normality, there's Adasin Darling, Komogorov Simonov. There are so many, but let me tell you this: each of those tests, they have their assumption too. So, and that's why when you are trying, but Shapiro wiki test is very, very popular that we use. But I also need you whenever you are actually using a particular test, look at the assumption around that. I'm working on a paper where I'm actually suggesting that before a court can entertain a case, courts should also give their own, what is the probability of committing error? Yeah, courts has to tell us. They are not perfect, because everything that we use in life has assumptions. Assumptions lead to limitations. So, and a module is as good as assumption put into a module. So I think that's a very good question. So we use a Shapiro wiki test because that will enable us to take a uniform decision across board, looking at the p-value. But the fact remains the Shapiro wiki test also have assumptions. Yeah. Okay, any other question? Anybody online with questions? Let me see my chat. Okay. Can you all confirm if you still hear me? Those of you online, still hear me, right? Did you hear that? Those of you online? Oh, I think, okay. Thank you for replying. Okay, this is where I'm actually going to stop today. Make sure you stay safe and have a lovely day. Bye for now.